Mega Mechatronics.
Welcome back to Mega Mechatronics. We are continuing Tuning 101 with part number 2. Let's get into this. We're going to be looking at knock. So, under normal circumstances, the spark plug ignites the air-fuel mixture, so the flame front propagates from the spark plug, and there's a nice pressure increase that pushes the piston down and spins our wheels. However, when we get into detonation or knock or pinging, we have these other ignition points, not just from the spark plug. So the spark plug may fire, initially ignite the air fuel mixture, and then there's like an instant, there's a pressure increase, and that pressure increase is lighting off the air fuel mixture at different parts of the cylinder. So if you look at a pressure, cylinder pressure versus crank angle, so that TC would be the crankshaft angle, and you can see when there's under normal combustion, there's a nice smooth increase and decrease, but when we start getting into knock, we get these pressure spikes, and then when you look at the intense knock, there's huge pressure spikes, which is very damaging to the engine, which can exceed the mechanical limits of the engine itself. So we have a controlled combustion clashing with detonation, and we start breaking parts, blowing holes through pistons, damaging ring lands, and possibly bending parts. And some causes of knock are just your timing is too advanced. Or you switch fuels, you went to a lower octane fuel, so the timing is too advanced for that fuel. You're running lean, so under low load, high load, you're a little bit too lean, and that changes the dynamics of how the stability of how that pressure increases and how fast those flame fronts are. And same with higher charge temperature, molecules are way more excited, they're ready to go, they're ready to light off. And also increasing the cylinder pressure because we're pushing those molecules together and there's more of them. So imagine like a domino effect or a chain reaction effect where stuff's a little bit closer so things go a little bit faster so you don't need as much timing. So ways to prevent, well, we need to log for it using the OEM sensors or aftermarket sensors, or we need to listen for it. So there's knock listening devices. You may see some professional tuners on the dyno with big headphones on. That's them listening for knock. And we also want to log our air-fuel ratio, because if you're under wide open throttle and you're getting knock, but it's because you're running a little bit too lean, and now you're retarding the timing and robbing horsepower potential. That's completely the wrong direction we want to go. So we need to make sure our fueling is perfect under those high load conditions. Other ways are to increase the octane rating of the fuel you're using. So go to a higher octane fuel, go to E85, or move into methanol alcohol injection. So we're trying to stabilize that charge. It's less likely to ignite, so it's a little bit more stable, where we have controlled ignition with the spark plug, and it's less likely to detonate by using a higher octane fuel. Summer blends work a little bit better as well. And to prevent knock, we can retard the timing, but like I said, make sure everything else is good, because once you start retarding timing, you are losing a lot of power. You're losing torque. So it's not the answer to all knock issues, but sometimes you just got to do it. And you can also enrich the fuel. So in some applications, forced induction, it can be very helpful. It can help cool the charge temperatures, and you're not going to lose that much power. So you find a good air-fuel ratio, then you add a few percent more. You're probably not going to see a whole lot of power loss. But you don't want to get too rich with gasolines and E10. You don't really want to go below 0.75 lambda, because you might start washing your cylinder walls and reducing lubrication and increasing wear. You can try to reduce cylinder pressures. Maybe you turned up the boost a little bit too much. You put it, that pulley you changed out on your supercharger was just, took it a little too far. So you may need to back that off. And as well, in addition, try to reduce the charge temperature. So going to a bigger intercooler can help you remove knock or gain timing to gain more power. Same with superchargers with their intercoolers, water, air, water that goes in between the supercharger and manifold. And that's a way to, you can even go both ways. You can try to increase your power. So you got your engine perfectly tuned, but you want to make a little bit more power. You can try to reduce the charge temperatures so that you can add a little bit more timing. And hey, now you got more power. So moving on, let's look at open loop and closed loop. And this is relevant for computer-controlled fuel injection systems. So under open loop, while the engine's running under open loop, the ECU is not compensating for errors in air-fuel ratio. So an engine's typically in open loop when you start it up while it's warming up, and also under wide open throttle. And some people will actually force open loop and run it that way. I guess you can do that if your application requires that type of running. But I'll show you why closed loop is going to be better. So with the open loop, it's relying on predetermined fueling data. So there's tables that it's looking up. So at this RPM and load, it looks at a table chart, says give it this much fuel. But it's not going to compensate for changes, for aftermarket parts, for stuff wearing out. So to visualize this, we have our command, which is an injector pulse width. But then there's nothing else. It's an open. The cycle is not complete. So that's why we call open loop, because it's just blindly feeding parameters, and it doesn't have a way to look to see what it's doing. So with closed loop, the ECU is compensating for error in the air-fuel ratio. So in closed loop, it uses real-time data to offset the predetermined fueling data. So if it's running a little lean, it'll offset that table so that now you're running perfect. So it's always going to try to target running stoichiometric. Because again, we're in closed loop, we're in idle, we're cruising, we're under low load, so we're in a closed loop, so it's going to try to target stoichiometric for us. So to visualize this, we have our command, injector pulse width, and now we close that loop with a feedback loop. So we're looking at the narrow band. So the computer looks at the narrow band and sees where it's at as far as air-fuel ratio, and then it makes small adjustments, adders or subtractors to that original fuel table. Now how we're going to do that is with fuel trims. There's a short-term fuel trim and a long-term fuel trim. So short-term is kind of an instantaneous fuel adjustment, where the long term is when the short term sort of exceeds a threshold and says, "Wow, I'm adding way too much fuel here to get our air fuel ratio. Long term, will you help me out?" And so the long term makes an adjustment. So they both add together to give you your total fuel. So let's visualize this. At the bottom, we have our uncompensated air fuel ratio. So let's say that's an air fuel ratio that's not stoichiometric. And our target air fuel ratio is our stoichiometric. So in order to move from the not stoichiometric to stoichiometric, we need some way to add on to that. So let's say you made a change to your vehicle and the old long-term fuel trim just not cutting it. It needs some more. So the short-term jumps in and says, "Hey, here's a ton of fuel for us." So it's doing a lot of the work. And this is before the long-term fuel trim learns. So learning is when the computer is storing this data in memory and making changes. So it's going to kind of learn. So after it learns, the long-term fuel trim will take up most of the slack. And then so the short-term fuel trim isn't doing all of the work. And it's sort of happy there, bouncing around that stoichiometric area. So this is after the long-term fuel trim is learned. So you can see how they both add together to get that same result, to get to the target air-fuel ratio. So these fuel trim, long-term and short-term fuel trim values are actual percentage errors in fueling. So a -5 fuel trim means it's 5% rich. So -5%. And we can actually use that to apply to our fueling tables. So it would -5% is going to take away from our offset adder. We'll go over that in different parts of the video. So a value of 9 in the fuel trim, that means it's 9% lean, +9. And of course, a 0 on the fuel trim means it's stoichiometric, means that you're doing really good. That tune's really good. So what you want to target is theoretically 0, but I would say you want to bias that to the rich side. So it is always safer to be a little rich, but the reason is because some ECUs will take lean fuel trims and add that percentage to your power enrichment fueling under wide open throttle. So if you're 9%, not +9 on your fuel trim, it's going to add 9%. So you're going to be 9% too rich on your power enrichment, and then you're going to pull fuel, and you're going to mess things up. So what you should really target is probably -2 to -5. And some vehicles, maybe you have to run it at -10 in some areas just because you changed out the injectors, you don't have the proper flow tables and the proper offset tables and all of those fine details. So it would be safer to run on the rich side than to run long-term fuel trims on the lean side. So looking at some more detail here and visualizing what the short-term fuel trims are doing, we'll go back to our chart here, rich and lean, and we're going to be logging air-fuel ratio over time. And so the positive, that's a positive fuel trim, and then negative fuel trim. So that's kind of showing the magnitude. So let's do a log here. And so what's going on is the short-term fuel trim is constantly making adjustments. So it's going rich, it's enriching, and then it's leaning out the mixture and enriching and leaning it out. So look at how much work it's doing. So it's constantly increasing the injector pulse width and decreasing injector pulse width so that it is bouncing around the stoichiometric area. So it averages stoichiometric. So it's constantly making tiny adjustments to compensate for that. So when we look at long-term fuel trims, here's an example here. So where the small peaks and valleys are, that's the short term doing its job. But what long term is doing is making big global shifts, let's say. So those 3 humps there are at a certain level. Then the long term fuel trim makes an enrichment, a change. Then you see how that sort of steps down for the next 3 peaks and valleys. You can see it's closer to our stoichiometric, and then the long term fuel trim makes another adjustment, and then lo and behold, we are bouncing around near stoichiometric, and the engine's happy. And if you look at the short-term fuel trims, and I have the oxygen sensor narrowband right below that, you can see that the short-term fuel trim is following the oxygen, or properly I should say, the narrowband oxygen sensor voltage is following the short-term fuel trims. And that's what we want. You can also see the correlation with the lambda sensor I have in there as well. So another type of input, and this is important for speed density type of tuning and maybe some spark tables. So manifold absolute pressure, what is that? So let's look at 1 atmosphere equals 14.7 psi. 1 atmosphere also equals 1.01 bar. And 1 atmosphere also equals 101 kPa, kilopascals. So psi, bar, and kPa are probably some units you are going to run across on forums and in reading and books and things like that. So we need to understand all of that. So 1 atmosphere. What is 1 atmosphere? That is 1 meter squared, a 1 meter squared column of air from the sea level, from the surface, all the way up into space when there's no more air molecules. So gravitational force is pulling down on the air molecules, and that is the pressure that we are measuring with 14.7 psi, pounds per square inch of pressure from gravity pulling down on a column of air. So another picture here, you can see the dots represent molecules of air, and near the bottom it's a little bit more dense. There's more air molecules, and when you get up higher, the air sort of thins out. So there's less molecules, it's less dense up higher. So what that means is the pressure, the atmospheric pressure is changing with altitude, because as you get higher in altitude, there's less air molecules pushing down at your level. So what the MAP sensor is measuring is actual atmospheric pressure. So when the MAP sensor is reading 101 kPa, it's reading 14.7 psi. And at idle, you're actually creating a low pressure area inside the engine, so you're going to be reading less than 101 kPa. And when you go full throttle and you open up the throttle plate, you remove that restriction. Now you're going to equalize the pressures. So the pressure in a naturally aspirated engine at wide open throttle should be close to atmospheric pressure. It depends on the efficiency of the engine. And with a boosted engine, you're of course going to go above atmospheric pressure. Let's take a look at a standard boost gauge. You can see it has two different scales. It has inches of mercury, which is the low pressure area or vacuum. And on the pressure side, we have PSI. And you see the needle is sitting on 0. This would be like the engine is off. Or in this case, we needed to take a picture of it, so it's sitting on a bench in normal atmospheric pressure. But what this gauge is actually reading is 14.7 psi. Or it's actually reading 101 kPa. Give or take a little bit depending on your altitude and what altitude you take this picture at. It's going to be around 0. So when it's reading positive pressure, when it's reading boost, it is adding its pressure on top of the current atmospheric pressure in the area, or approximately 14.7 psi. So when this boost gauge is reading 10 psi, the engine is experiencing 24.7 psi, which is 10 plus 14.7. So moving on to another input is our mass airflow sensor. There are two types. We have our vane meter. So this is like a mechanical door. So where the airflow pushes the door open. So the more airflow you have, the farther the door is going to open, and that correlates to more airflow. And this is actually an obsolete technology. So we have our vane down there. So this vane is kind of opened a little bit, and we have a picture of an actual one on an illustration where the vane is closed, in the closed state. So you can see that as the engine requires more air, it's going to push that door open farther, and then there's a little potentiometer or something measuring the angle, and that'll correlate to some airflow. And it's got its issues, and temperature and humidity and all those different things will affect your readings. It's not that great. So the current state of the art will be the hot wire sensor types. So we have a heated wire in the path of the airflow. So as the air passes over it, it cools down the wire, which changes the resistance. And usually they have an integrated temperature sensor. So here's an example of a hot wire, and you see that wire there. You can see here's like a cleaning cycle. So the wire, got red hot to burn off contaminants, but you can see that's technology. So the wire heated up, air flows past it, changes resistance, and that will correlate to an airflow measurement. So some more inputs, other OEM sensors, and these are all very important and things we want to look at. So ETC, that's the throttle, or the throttle position sensor. The RPM, revolutions per minute, timing, intake air temperature, the injector duty cycle, to see if we're maxing out the injectors, our cylinder air mass. We might want to look at that to do some Kentucky windage tuning. Command X. So that's a command of, let's say the ECU is commanding an air fuel ratio. We can see that. Or we could see the what the ECU is commanding as far as boost. Or it's what is it commanding as far as torque and things like that. So that's what I mean by command X, where X is fill in the blank. So fuel pressure, we need to see, is the fuel pump keeping up? Do we have a pressure drop? Coolant temps, oil temps, all those temps are very important in oil pressure just for engine safety.